This is Group 10, Properties of Aluminum and Iron, Project number 2,
by Josh Webb,
Patrick Nimina,
and Owen Champion. Interatomic distance. So finding the interatomic distance requires a derivative of the Lennard-Jones potential set to 0. d E total over dr equals 0. Computing the derivative, we get d over dr equals negative 12a over r to the 13 plus 6 times b over r to the 7 equals 0. And then we plug in the values for A and B for aluminum. A equals 5.841 times 10 to the negative 10, and B equals 2.392 times 10 to the negative 6, which were given to us. After plugging this into the equation, we get that the interatomic distance for A, for aluminum, is 0.296 nanometers. And if we plug in the values for A and B for iron, we get that the interatomic distance is 0.3 nanometers.
interatomic distance of aluminum. This is the Nike function of aluminum. This shows at a distance of about 0.245 nanometers, the energy total is positive, and after this point, the total energy remains negative and will never touch 0 again. The depth of the minimum is how strong the bond is, while the curvature, how steep the sides are, shows how stiff the bonds are. Finally, the minimum also shows the equilibrium interatomic distance, which for aluminum is 0.28 06248 nanometers. This is found by taking the first derivative and setting it equal to 0, or by finding the minimum of the Lennard-Jones potential. Graphing the interatomic distance of iron. This is the graph of the interatomic distance of iron. Just like aluminum, the interatomic distance graph of iron has the same properties as it. However, the atomic distance is 0.2825256. Iron still has a stiffer bond even though the slopes of the materials are the same. This is due to the well depth of iron being deeper.
Alright, now let's look at modeling and finding the elastic modulus. So the elastic modulus of aluminum and iron requires the double derivative of the Lennard-Jones potential. This leaves us with the Nike function above. The material, basically, when we look at these graphs, the material with the steeper slope will be stiffer, and the material with the shallower slope will deform easily or more easily. So in this case, you can see that right down here, iron has the steeper slope and aluminum has the shallower slope. Alright, next we will be looking at the bulk modulus. Basically, the bulk modulus measures how much pressure is needed to compress a material uniformly. So for iron and aluminum, it's calculated by looking at how the energy between atoms changes as the distance between them decreases. So when you take their interatomic potential and you find the derivative of energy with respect to the atomic distance at the equilibrium spacing, this shows how steep the energy curve is and when atoms are pushed closer. So you can see that right here in the equation, which is right here. So this is our finding the derivative right here. Sorry for that. It's a little sloppy, but we'll live. And next, you have to then relate the volume change by dividing the atomic spacing, which gives you ultimately your bulk modulus. And it's going to give you it in energy per volume units, so you just want to make sure that you convert that to gigapascals or GPa. So when we look at the final results, iron is stronger, or I mean iron has the stronger atomic bond, and thus it has the higher bulk modulus than aluminum. All right, next we are looking at vacancy concentration. And before we get into our equations and everything, first let's talk about what vacancy concentration is. Vacancy concentration is the fraction of atomic sites in a solid that are empty. Basically, it's the chance that a site is missing an atom. So when we look down here on the graph, we see our formula, which is N. N is going to be our atomic site per meter cubed multiplied by negative QV, which is our vacancy formation energy right up here. And then it's divided by our K, which is our Boltzmann constant, and it's multiplied by T, which is temperature, which is in Kelvin for this. So when we look at our equation or formula here, we see that vacancy concentration relies heavily on temperature and the formation energy. So it relies heavily on T and QV, meaning that the higher temperature that you have, the more vacancies you'll have. And the higher formation of energy that you have, the fewer vacancies you'll have. So the higher the temperature, the more vacancies. The higher the formation of energy, the fewer vacancies. Now let's look at our vacancy probability, which is right here. Now for this formula, it's a little different than our vacancy concentration because we don't have our atomic sites per meter squared. Basically, it's just the vacancy formation energy divided by the Boltzmann constant multiplied by the temperature, which is K, and the vacancy formation energy is still negative for this one too. And basically what vacancy probability is that it's the chance an atomic site in a crystal is empty. So this basically means that it only exists in a specific position, excuse me. So when we take all of our information that we've gotten from this lab and we plug it into both formulas, you see that for the one on the left, the vacancy probability, we see that aluminum has a much higher vacancy probability than iron does. And if we look on the right, we see that aluminum has a much higher vacancy concentration than iron does. So, yeah. Now, vacancies and yield strength have direct correlation. So, vacancies, as I said last slide, are missing atoms in a material structure, and they make it easier for atoms to move when stressed. So, when we look at the impact on yield strength, because aluminum has more vacancies than iron, it tends to deform easily, which leads to lower yield strength. So if you look down here at aluminum, higher vacancy concentration, more diffusion pathways, which equals lower yield strength. Iron, because it has fewer vacancies and stronger bonds, it resists deformation better, so it has a higher yield strength. So look down here, lower vacancy concentration, fewer atomic disruptions, which equals higher yield strength. So the more vacancies generally means the lower yield strength that you have. Thank you for watching. This is Group 10's Project 2.